All right, everybody. So I just want to talk about some general ideas on this lesson as a whole. I know this lesson was very long. It was fairly complicated. And I just want to tell you kind of two ways to think about approaching this. So one way is just, I want to pass this class. I want to get the answers right. I want to get a good grade. I want to move on. I don't really want to think about the math too much. That's okay. If that's your perspective, if that's what you have time for, if that's your priorities right now, you do you, you know yourself, and at this point, if that's where you are in life, that's okay. So, get online, do your homework that your teacher assigns, um, and get through it with the help of some of these examples that I've given you. Now, if what you want to do is understand these problems, just like get a better grasp of them, feel more comfortable doing them outside of just a few homework assignments. So if you're in my class, kind of speaking directly to my own students, not Mr. May or Mr. Calkin's students at this point, but for my class, those of you who are in ALEX, you're working in ALEX, and you have extra credit opportunity to do Learn Mode, you can go into Learn Mode right now, and you can work on some of the problems with factorials if you want to get more comfortable. If there was a part of that explanation where you just weren't really latching on to, like, what is the factorial formula? Why does it work? You can go in, you can find problems in the top bar in Learn Mode that are labeled as factorial problems, and you can get more experience there. So you can get more comfortable with this topic and at the same time be earning extra credit. If you don't want to do that, that's fine, but I think that would be a great option for somebody who's interested in this or for somebody who wants extra credit. Now, the other thing I want to say is that this topic is very broadly applicable. Like I was saying before, it deals with any kind of situation where there's two outcomes and you're going to repeat that process of having two outcomes over and over. So I can't really name all of the ways that you could apply that, but it's a very general kind of principle. It takes the form of a long explanation, but once you get comfortable with the pieces that make up that explanation and you can put them all together into that binomial theorem, then you have a really strong tool that allows you to just quickly create calculations that answer a whole variety of types of questions about probability distributions, about how likely do I think some kind of event ought to be based off how likely the events going into it are. Okay, so it's all just about understanding probabilities and how they deal with each other. Okay, now what I would like to do is talk to you about one other thing. If you want to get off now, this is the end of the lesson. If you want to stay on, what I'm going to talk about is Pascal's triangle a little bit more, and we're just going to talk about some kind of crazy stuff that's going on. If you remember in the lesson, I said that you could find all the coefficients of the binomial expansion within Pascal's triangle, but that I personally have no idea why you can find them in there. Well, that's not the only thing I have no idea about. There's quite a list of things that I've got no clue about that I'm pretty interested in trying to figure out for myself. What the heck is going on here? So let's go through them. So here's a post that's the top 10 secrets of Pascal's triangle. So we build Pascal's triangle. We understand how to do that. Now let's look at some hidden sequences. So if you push all the numbers to the side, this just kind of makes an arrangement that's easier to show some of these properties. So if you push them all to the side, so it's not like a triangle, it's not an equilateral triangle, it's a right triangle now. The first column, not too interesting, it's just ones, okay? Second column, sorry, the 0th column, the starting column, all ones. The first column is natural numbers, just counting, okay, nothing too complicated. The next column is triangular numbers. So if you imagine drawing a triangle, so let's draw it out of 3 dots. So like you could have 1 dot, and that could be, I guess that's how I want to say it. Let's go to 3 and 6. That's better. So if you have 1 dot and 2 below it, that makes a triangle shape, right? 1, then the next layer is 2, so it adds up to 3. If you put 3 down below that, you would add up to 6, and that would be a larger triangle. You could put 4 down below that and make an even larger triangle. So that's what's happening here. You have triangular numbers encoded into Pascal's triangle. So you have triangular numbers here. The 4th column are tetrahedral numbers. So these are not triangles, but pyramids. So if you think of, let's start with 4. If you think of like 3 balls and then 1 ball sitting on top of it, then you have a pyramid shape, right? A pointed pyramid shape, kind of made of round pieces, but you have a pyramid. If under those 3 balls you put another 6, so basically what we're doing, we're taking these triangles, the triangle of 1 object, 3 objects, 6 objects, 10 objects, and we're layering them on top of one another. So 1 on top of 3, on top of a larger triangle of 6, on top of a larger triangle of 10, and that's what's the tetrahedral numbers. Past that, we get into like abstract ideas because we're no longer, this was a 2-dimensional shape, a triangle, a 3-dimensional shape, a pyramid. After this, you'd still have the same kind of conversation you could have, but you're talking about 4th and 5th dimensional objects. The columns continue in this way, describing the simplices, which are just extrapolations of this idea to arbitrary dimensions. So arbitrarily high dimensions. All right, another secret in here, powers of 2. If we sum each row, so take all the numbers and add them up, we get 2, 4, 8, 16, 32, 64. We get all the powers of 2. That goes on forever. If we take the numbers and we just read them, 1, 11, 121, 1,331, 14,641, that is powers of 11. Why are these things in here? Why is the powers of 11 here? Why are powers of 2 in here? Why are triangular and tetrahedral numbers in here? There's another, perfect squares. If you look, how does this one go? So we can look at perfect squares by summing 2 numbers, summing 2 numbers to the right with the number below the number to the right. Okay, so we're saying that 4 squared is 16. 3 squared is 9. 2 squared is 4. So any number here, if you square it, you can get to that number by adding the 2 numbers to the right and to the left. So, only in column 2. Okay, so these numbers in column 2 here, column 2, column 1 vernacular kind of getting mixed up. But anyways, if we take the numbers here, 1, 2, 3, 4, 5, and we want to find their squares, so square of 2, square of 3, square of 4, we go over 1 and down 1, and we add those 2 numbers. So 1 and 3 is 4, 3 and 6 is 9, 10 and 6 is 14. What the heck? Why is that in there? Have you ever heard of the Fibonacci sequence? That's something where you start with 0, then you take 1, then you add those 2 numbers together, so you get 1 for the next one. So now your final numbers are 1 and 1. You add those together to get 2. Now your final numbers are 2 and 1. You add those to get 3. Now your final numbers are 3 and 2. You add them to get 5. Well, if we line them up like this and then we look at them diagonally, we get the Fibonacci sequence. 1 and 1 makes 2. 1 and 2 makes 3. 2 and 3 makes 5. 3 and 5 makes 8. The Fibonacci sequence shows up in the real world in like all sorts of natural processes. So there's some sort of property where I'm not going to be able to describe it very well because I haven't really looked into the Fibonacci sequence anytime recently. But it's just sort of a simple property of like, if you kind of has to do with like triangles, and some of the side lengths of a triangle share the hypotenuse of the other one, so you can kind of make some arrangement that follows that pattern. Anyways, it basically models like shells that grow, like broccoli stalks. You get these Fibonacci sequences of objects where it goes, what did it say? 1, 1, 2, 3, 5, 8, 13. The Sierpinski triangle is kind of cool. So if you take all the numbers in this and you shade in the odd ones and you leave the even ones unshaded, you end up with the triangle from Legend of Zelda, basically. So it's this fractal where it's a triangle made of 3 triangles, each 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 made of 3 triangles, on and on and on forever. So this is what you get if you shade in all of the odd numbers. So 1 at the very top, 1's down the sides. You end up with this fractal image. What else? Combinatorics we've gone over. So different types of combinations. 3 choose 1. This is a different notation, but this is 3 objects choose 0, 3 objects choose 1, 3 objects choose 2. This is the property that we were using a lot. Okay, expanding binomials, you do that through using those, through using these, and we already went through that all today. Binomial theorem, did all that today. Okay, so what I want to get at here is like, this is this little object. All it is a simple pattern. Take 2 numbers, add them together. Take 2 numbers, add them together. Take 2 numbers, add them together. But there is so much in this. It's mind-blowing. There's so much stuff to be discovered in this. There's probably more than those 10 things. And I think what I would like to direct your attention to is they all share this structure, this object, this triangle that was built. All of these different concepts must not be so different from one another after all. Powers of 2, powers 11, square numbers. There must be something about all of this math that is kind of similar because they all share this object, right? If they all share this object, there's got to be something about this object that kind of lets these concepts talk to each other, that lets you move from one concept to another. What I guess is I'm trying to say is, like, I think what's going on is there is some even simpler thing in here, some really simple description we could make that we could follow to all these different conclusions, to all of these different, 10 secret properties. Just in the same way that, like, in science and chemistry, you can take simple combinations of protons and electrons, and you can make a million different types of molecules, and those molecules can make millions of types of larger structures and organs and organisms and creatures living, thinking. You can get all of this incredible complexity in science from really simple foundations. It's the same thing in math. You can get a ton of complexity from just like one little idea. And that kind of funneling, that idea that there's all these different concepts, but they really all just funnel down to one idea, that's what inspires me in learning about the world in general, whether it's math, whether it's science, whether it's English or history. It's this idea that, like, this complicated world can really be focused down into simpler ideas that produce all the beautiful complexity that we see. But it's like that search. It's that search for that deep down idea, that deep down property that makes me excited to learn new things. Because every time I learn something new, I feel like I'm either, establishing another branch and understanding the picture more fully, or I'm connecting branches and I'm seeing how two different topics really are talking about the same thing in two different ways. And the more that you can connect those branches and fill in that, tree of ideas, the closer you can get to that fundamental, like, what is going on in the world? What is all this stuff, and why is it all happening? So, that's why I'm really excited about this lesson. I know it was a long one, but I think it's cool. And I think it, especially here with this Pascal triangle, which we didn't spend a ton of time on, but there's just so much that you can get from a simple idea. So I hope you got some of it anyways. I hope you got some of those ideas that I was trying to get across today in this lesson. Thank you for watching all of these videos. Thank you for putting in time and effort. It will pay off in your future. You will be a smarter, harder working, better person for it. So congratulations on making it through today's lesson, Powers of Binomials.